So we'll be here talking about applied responsible AI in algorithmic marketing. Our goal is to light up the spark on your responsible AI projects if you still haven't started to do this. So that will be the first goal. The second goal is if you have started, we would like to have a feedback loop and try to make a conversation with you, because this will not be a complete solution, not at all, and it will be much focused on requirements that we can solve more or less alone as a data scientist. So we'll have some technical content for you, okay? Okay, so I'm quite sad when I heard talk about responsible AI framed into a regulation problem. That leaves me quite sad, because it could be much more than that. Responsible AI should push us to be better in developing our products. And that's what I think that McKinsey tries to convey on this report on a survey that they did to more than 2,000 companies, where they tried to profile companies on responsible AI, data privacy, cybersecurity. And they say that companies that have good practices in these three fields, they are 1.6 more likely to create, to have growth rates of revenue and a bit 10% more than the other companies. So that's one way to put it. And the other way to put it is that they also lose less. So they have less AI incidents. And what they explain is that they can do that because they have a set of practices that are installed on their teams, and they can do better than the other companies. So at the end, what we should understand is that responsible AI would push us to have better products that deliver more economical value to the company and more value for society. Okay, that's my first point, and that's why perhaps a telecom company like NOS is also here, because as probably you would say, NOS would not be a company for high stakes use cases on this field, right? So the next slide puts a question on what's holding you back to start consequential responsible AI practice. And when we think about this, we usually think about three things. The first thing is that, okay, some magic is going on my organization, and someone will take care of that, okay? And probably that will be one of the questions that you have for us. Who's responsible for responsible AI? I would say that we are all responsible. Of course, there will be more people responsible than you, but even so, you have a responsibility on the work that you do as a data scientist, for instance. The second point is, okay, perhaps that's important, but I'm not working on an industry which has high stakes use cases. And you can think about telecommunications, gaming, and so forth. And for this point, I would say that you can't dismiss it, because even on those industries, you have high-stakes use cases like hiring, like managing the debt of a customer, like deciding if a customer is going to trial because of the debt. And those are high-stakes, or at least medium-stakes use cases. And the other point is that even if you don't have these medium stakes, perhaps you're not finding other high stakes because you're not practicing. You don't know how to do it. So how do you know if you have or you don't have an high stakes when you're not doing responsible AI? So you need to practice this, okay? And the third point is that, and this is where we're going to depart, is that you know that is important, you would like to do it, but you don't know how to do it, because it's such a scattered field and disciplines, and how can I connect the methods? How can I discover requirements? So we'll try to shed some light into that. And the way that we kind of created this talk is to start doing that in something that you can control as a data scientist. So there are different roles on a project, like these ones, data scientist, domain expert, risk expert, regulator, and the end user. And all of them will have different requirements, different concerns for responsible AI. And those ones, those are familiar for you as a data scientist. You want to understand the model, you want to debug the model, you want to troubleshoot it. So for sure you have ideas how to do that. And one thing that we, of course, we would like to suggest, and that's great that Sarah already did this job for us on the previous talk. You need to know the principles, which we brought a different framework. It's from Alan Turing, but as Sarah said, it's okay. I like more this one because it's easy to memorize. It's fast. You can memorize fast very quickly. And you need to come down from these principles, which are big, fluffy and abstract, and goes down to the pyramid. So you need to set up goals, you need to translate these into requirements, and then you need to have a practice that implements these in tools and practices. And one of the questions that was thrown to Sarah was if there is any framework where you have perhaps questions that could guide you through the process. Yes, there is. Microsoft just released last year a general requirements document which has a lot of questions and goals and requirements that you can go through to elicit these on your projects. Okay, so there's a lot of frameworks and there's things that are like this that you can use. Okay, another thing that we would recommend is to make some research, because at the end you need to know more of this. You need to go down from these principles and you need to understand how they connect to topics that you can develop some thinking and then reach a method that you can implement. For instance, transparency is not only explainability and AI, but this is something that we can tackle. And with this concept, we reach another concept, which is the question, how can I explain, which are the goals of explanations? What do I want to explain? And with this, I can connect this with sustainability and fairness, because explainability is just an interface to look at things, okay? And when I'm doing then my research on sustainability, I can connect this with robustness, and then I can reach a method which is adversarial robustness. So I want to explain, to justify, and I can do that using this method. And doing this kind of, concept mapping, perhaps you can find those concepts and methods for you that would work out on your projects, okay? Well, you need to do this, or we need to do this, not in the void. We wanted to present you a use case where we are using this. The use case where we are using this is, we call this smart pairing. The idea is very simple. So we have customers that are calling to our call center, and these customers are calling us not for the best reasons. They want to disconnect their services. And our job is to make sure that the human variable that we have at our disposal on the call centers is best used in the best sense, in the sense that we can pair the customer with an operator that fits better the goal of the call, okay? And that's what we are doing here. And then the implementation strategy is quite simple. So we have customers, we have assistants, we have features from customers and assistants, and we have a task of predicting the lifetime value of the customer at each pairing possibility. We train a model with this, and then at inference, what we do is we get the call, we try to understand how many operators are available, and from those operators which are available, we would see which are the best outcomes, and then we can rank with a strategy, okay? That's what we do. So the first meetings that we have with our risk management team, they were quite good, and they had this requirement that we need to solve. And probably would say that's not a requirement, that's just a sentence. That's true, and that's the difficulty. You need to pass this to a requirement which is implementable. And so we could do one thing, which is you can get away with an answer, which is, okay, I need to use ML because I cannot predict with an average, I will not have business case, or I could do cluster analysis, but that's not okay as well because it's too coarse. So I need ML point. But it's not the way that I think that we should answer that. We could do better than that. And the way that we did was to devise a strategy to test algorithms with different complexity. So we know that we have algorithms with different complexity at our hands, and we can use them. And with that in mind, we can then confront those algorithms with different metrics, and metrics that could represent different dimensions of the principles that Sarah just showed us before: robustness, fairness, and transparency here with quality of explanation. So the idea that we had was just to break down this, let's say, big requirement into 3 questions. The first question regarding performance/fairness. We want to understand where the model is failing, which are the cohorts where the model is failing more or failing less. We want to understand what happens with explanations when we are comparing explanations that are coming from different models. And we want also to understand how the model is reacting when we are perturbating some data points that the model didn't see. And armed with that, we created this framework and we did that strategy execution that Rafael is going to show now.
So the first step on this strategy is actually evaluating global performance, which I'm sure that it's something that you're all familiar with. But here I would like to add a little remark. There's this idea that interpretable models, they have interpretability at a cost of something, that we are losing predictive power when we increase the interpretability of our models. This is very much context dependent. If we have a data set that is well modeled with a linear regression, then using a more complex model is just adding unnecessary complexity. So it's kind of our job to prove that in our specific solution, we actually need a more complex approach. And we actually don't have to choose sides. We don't have to choose whether we're just going in the interpretable route or the black box model with a post hoc explanation put after. We can actually train both interpretable and explainable, these models that are black box but can be explained afterwards with approximations, and then evaluate and try to justify which one we want to select. So if we go to performance in this particular use case, we selected for our interpretable models additive models with increasing complexity, starting from linear regression all the way to an EBM, which is again with pairwise interactions on the most important pairs of interactions. And we actually verified that indeed our XGBoost model was getting a better performance on the test set. But when we look at the top contendants in the interpretable side, we see that EBM is 5% off our target set by the XGBoost. If this was all the metrics that we considered, this would be the end of the story. We pick XGBoost and we go to the next project. But we do a little bit more than that. So associated with global performance, there's something that's kind of hidden in these aggregated performance metrics, which is the local performance that our models actually have. When we have our feature space, we can be in a situation where the error is kind of uniformly distributed across the feature space, or we can be in a situation where in some regions of the feature space, we have a high amount of error, and in some regions of the feature space, the model actually models quite well the relationships between the targets and the predictors. So it is important to actually try and understand where our models are failing and why our models are failing. To do this, we trained regression trees built on the residuals of the models that we trained, and then we interpret the subsequent residual trees and try to extract some information and profile both our models according to this evaluation. So this does two things. We get the nice residual trees that we can actually interpret. This is an example of one. And if you looked at the generality of them, one of the things that we identified is that customers with higher paying packages were actually being a little bit harmed by the decisions of the model since they were more prone to error. The same thing with operators that were getting more inbound calls. And this led us to set a little alert that allowed us to introduce more variables regarding customer churn and develop other strategies for correcting the performance of the models in these regions. There's also the second part, where we can actually look at the cohorts of error identified in each one of the models and try to see which ones have the highest disparity in terms of error and prediction quality. And we actually see that although a small difference, XGBoost actually performs a bit worse in the percentual wise when compared to the baseline of the performance. So what about explanations that we can derive from our models? One of the common ways that we can derive explanations from models is through feature importance. The idea is that we are trying to get tokens that somehow tell us how important a certain feature is in the decision of the model. But we have to remember that these are actually built on certain assumptions and are mostly approximations. It's not something that's derived from first principles out of the model. So they must be also evaluated. There are three things that we can use to evaluate an explanation. We can go for application-grounded, human-grounded evaluations, and functionally grounded evaluations. Now, application-grounded and human-grounded evaluations are evaluations that center themselves on the human side. Here, we try to see how well a certain human can, for example, understand the decisions that are being made if the explanations build trust in the model, and if a human can reproduce the decisions that the model is making with the explanations that they are given. And then we have this third group, which is quite interesting, which is called the functionally grounded evaluations, where we're not really focused on the human side. We're more focused on seeing specific properties of our explainer. So here, for the feature importance, we use the metric called monotonicity of feature importance, which is available in this paper right here. And the idea, I'm not going to bore you too much with the mathematics behind them, but the idea is that if a variable is more important, then if I had to guess the true value of that variable for a given observation, I would have a higher variability of the predictions. Here it's useful to actually think of an example to build a bit of intuition. So if a feature importance, if a method gives me a feature importance of 0, I would expect that changing that specific feature to another value of its domain would give the same model response. On the contrary, we could also expect that on the opposite end of the spectrum, if a variable has a very high importance, then if I change the true value of that specific variable for an observation, I should have a large fluctuation of the prediction that is being given. So we can actually measure this, and when we do, there's the algorithm right there. I'm not going to delve into this very much due to time constraints, but I would like to focus your attention here, where what this metric allows us to do is that when we have two or more methods for extracting feature importance, and they're kind of conflicting, some are saying that some features are important, some are saying that some are not, we can actually have a way to think and build some criteria to choose which ones we want to go with. There's also another important note that if we look at the best performing feature importance methods alone, we can see that XGBoost seems to be lacking behind the EVM model. And that means that our predictive performance is kind of coming at a little cost of the explanations that are being extracted through feature importance seem to be less accurate according to this criteria. So the last thing I would like to talk to you about is adversarial attacks and how we develop the strategy for this in our implementation. And the idea behind an adversarial attack is that we have some observation, and we try to find this small perturbation that creates a new example, which is completely evaluated in a different way by the same model. We try to follow an approach here that is centered on optimization problem. So the idea is that we try to define an hypersphere around a certain observation, and we try to find which point in that specific hypersphere has the highest loss when compared with the point that we had. And what we realized when we did a sample of different points and created a lot of adversarial examples for each one of the points is that the adversarial examples extracted from XGBoost were actually a lot more erroneous than the ones that were extracted by EVM. Now, the idea is that this is somehow telling us about the numerical stability of our decision function, meaning that if we have a new example and it is close to an example that we see in the train set, if we have a very low adversarial error, we can expect that there won't be many fluctuations on the prediction, and we have a prediction that is somewhat similar to the one that we had for that specific data point. So, at the end of the day, you'll get something like this. So instead of having just the model performance, you kind of extend a bit of the evaluation of your models to actually include some other metrics that can be relevant for you to actually understand how your model is behaving. So you could see that when we started, we had this idea that XGBoost was just overall better in terms of performance, so this should be the model that would be selected. When we look at something like this, we can see that performance kind of comes at a little bit of a trade-off. And now there's no magic solution to which model you would pick. It depends on the application. It depends on the level of comfort that you and the people responsible for your data product have on sacrificing some of these aspects. But having this as a tool of comparison is important because it actually tells you a bit more about your model, and you can extract a bit more in terms of the general knowledge of your model. So.
Okay, so we're out of time. Just to wrap up, what's coming next for us? So we want to lower the effort on adopting these on the projects. So we would like to streamline the process in order for the data scientists to include these very easily in their processes. Then we would also like to include responsible AI in our learning path. That would be also important to get more debate around metrics and these approaches, because this is a starting point. It's very critical to do this. We could do it in multiple different ways. And we want to keep pushing applied right to projects. We need to have more patterns. We need to discuss these in other contexts. We brought you an idea of how to apply this without having a lot of context dependence. And I hope that's really worth your time. And the question that we leave you is what comes next for you, while implementing responsible AI at your company or your organization. Feel free to throw us some questions. Thank you for your time. Hey, Alice.
Thank you. Yes, thank you so much. So I have here some questions from the audience. First, congratulations on your work. So you can still submit questions and vote on the ones that are here in the applications. So the first one that is here more voted is related with, a little bit with the use case that you showed today. I think it's a bit related with this ethics evaluation of the use case itself. So regarding this optimization of the disconnection from the service or the churn of your clients, if overall this is a problem, a use case that is within the responsible AI or within the ethical framework of problems that should be addressed by AI. We know that it is one of the biggest problems that is solved by AI, so predicting the churn and so on. But I think the question here is a bit related with the assessment that you make on these ethical questions before even starting a use case.
Okay, so the question is, if this use case, we should apply responsible AI or...
Yes, they ask if it's transparent to the customer, or if you think it could be a bit manipulative, or if you are respecting the customer privacy. So these questions that when you are setting up a use case,
for sure. Yeah, sure. I think, okay, so in terms of the legitimacy to implement this with data that the customer supply to us is of course legitimate, because we need to solve a call in terms of service, and the customer sign documents in order for us to use that information. And then I don't know exactly what's the ethical question there, but I would say that you can think about the counterfactual of not having this. You might think about one operator that is receiving a call that there is a very high cognitive effort for him. And with this recommendation, you could adapt this cognitive effort because you can adapt a better call for that operator to pick up and to manage. So I think that if you think about that, and of course you need to have more questions. This is not a full-fledged implementation on the requirements that you need to do in order to close in order to have all the right implementations closed. But I think that if you think about other things, such as at the end of the day, the system shouldn't distribute the calls unevenly. So I should have more or less the same number of calls. I should have more or less the same number of calls that have different effort for the different type of operators. So there's other things that we are looking into and are not here placed, because I think that probably it's less portable, and we only had 20 minutes.
And it was a bit an example to illustrate your process
Yes.
of evaluating. And you have this first question: why do we need AI? Why do we need a model? Right?
Yeah. Yeah.
Okay. Nice. So we have here a more technical question regarding functional interpretability or explainability metrics, and if you should compute them using the training set or the test set. So it's a bit more detail.
Yeah, the way that we did it is that we did it on the test set. I'm not really sure. You could try to do it on the train set as well. I think it comes to a point that it's close to using some metric on the train set and using some metric on the test set for performance. If you do it on the test set, you are kind of seeing the generalization of that metric on data that has been unseen. If you do it on the train set, you are using the data that you already saw. So in my opinion, I think it might be more useful to do it on the test set. But I think that's